Hello, my name is Ben Schurman. I'm a senior here at UMD, and today I'm going to talk to you about my experience modeling eclipsing binary stars with Professor Dan Stevens. Before we get into what that entails, here's a very brief introduction to myself. I'm a physics major and an astronomy minor, and I'm finishing up my 5th year here at UMD. Inside of school, I enjoy learning about astrophysics and coding. However, outside of school, I enjoy stargazing and being in nature with my friends, as well as taking pictures of northern lights, as you can see here. But you're not here to learn about me, so let's move on to the big question, which is, are lower mass stars actually larger and cooler than what stellar models predict them to be? Now, when I say lower mass, I am referencing stars that are about 10 to 60% of the sun's mass. These stars are called M-dwarf stars. Now, the problem is that we are measuring their radii to be about 10% larger than what stellar models can predict, and on a similar note, we measure their temperatures to be about 5% cooler than predicted. These figures on the right show the observed radii and temperatures over the predicted radii and temperatures, and as you can see, there's a noticeable trend going on. So, is this the case? Are they actually larger and cooler? Or are binary star interactions such as tidal forces actually influencing our measurements? Now, to understand what that means, we'll have to dive into eclipsing binary stars. So, what even are binary stars? Well, to put it simply, they are just two stars that orbit a common center of mass. They consist of a primary hotter star and a secondary cooler star. There are eclipsing binary stars, which are special because all they do is they eclipse one another from the perspective of Earth. This top image shows the top-down view of an eclipsing binary, or EB for short, and the bottom image shows them eclipsing from our perspective. Now, there are two types of EBs, a double-lined eclipsing binary, in which the light spectrum of both stars are available and visible to us, but we are concerned with single-lined eclipsing binaries, where one of the stars is so dim that we can only see the light spectrum from the brightest star.
You might be wondering, what's the big deal? Well, with a DLEB, with the spectrums of both stars available, it is actually possible to determine the individual masses and radii of both stars. This is done by observing the change in brightness during the eclipses, as seen on the right here. This allows us to determine the sizes of both stars based on how much the brightness changes. Now, with a radial velocity measurement, as the stars move towards and away from us, we can also figure out the masses of the stars. But to do this, we need both light curves from both stars. So in the case of an SLEB, we can't do that easily. We require an external measurement of a star's mass or radii, or in our case, we can actually model this. So this is where I come in. I'm creating a model that uses inverse modeling with a given set of SLEB parameters, such as the masses and radii, to predict the eclipse and radial velocity observations. Now, existing methods to do this can take days or even weeks to find the best fit parameters with their errors. So we were wondering, can we do this faster by using Python with the exoplanet package? This leads us to HD 74925, which is an eclipsing binary with an 18-day orbital period. Stevens et al. Previously determined the stellar and orbital parameters of the system, such as the masses, radii, and orbital period, by using ExoFast v2, which is IDL-based. Now, the figure on the right is the light curve, showing the primary eclipse in the middle. As you can see, it's pretty flat, except for that one dip. Now, if we had to consider factors such as shorter orbital periods, variable stars, or tidal forces, these light curves would be a lot harder to understand, which is why this is a great starting point. My work has consisted of building and tweaking a model that gives results that match our light curves and radial velocity curves that we have as inputs. This figure on the right shows an example fitted RV curve for HD 23642, which is a different EB to test if the code can indeed generate an RV model, which, as you can see, it does pretty well. However, there's still a lot of work that remains to be done. Once the model can predict the physical parameters of the system, we want to know the uncertainties. This can be done by doing a Markov chain Monte Carlo, which, to put it simply, involves iterating the model many times over and checking how likely the outputs are. What I mean by this is it runs a model, but slightly changes the inputs each time, and it checks, again, how likely the outputs are. Now, this allows us to understand the uncertainties of our physical parameters. Once we're able to do this, we can compare the physical parameters for the same system but modeled differently, such as an exofast V2. Once this is in place, we can perform comparisons on increasingly complex SLEBs, such as those with tidal forces. And then from there, we finish up the UROP. With that said, though, there still is a lot of work that remains to be done. There has been numerous setbacks along the way, but this isn't going to stop us from getting answers as to whether lower mass stars are indeed larger and cooler than what stellar models predict. So I'd like to thank you for tuning into my talk. I hope you have learned something interesting about eclipsing binary stars, or really anything about space. So thank you again.